after class. If not, I'll bring them on Wednesday, okay? But the grades should be up. Can anybody confirm that? All right. Now the grades are, I don't know what the average is, but there's a whole lot more higher grades, I can tell you that. And I'm happy about that. All right, now, next. Questions about anything. The quiz solutions are up there, are they not? Anybody confirm that? Anybody? On one up, can you see them? Yeah, okay. It was literally a template problem. It was a homework problem with change values. That's all. And please keep up with this stuff. Now, we're going to cover inductors today. First, are there any questions about anything from the homework up to now? I mean, everything we've done today. Anybody? Yeah.
I was thinking about question 4.38.
Is this with inductors? Or?
Yes.
Okay, yeah, why not? I'm going to outline this first. Now, let me give you a little history. I know I was kind of rushed on Friday. Inductors and capacitors lead to only first-order differential equations, the solution. I have to say one other thing. Some of you are probably thinking in your back of your mind, are we going to have circuits with inductors and capacitors in them? Those would have second-order differential equations. We are not going to cover that. So I didn't get that question yet, but it should be in the back of your minds because, most systems, a lot of systems in mechanical engineering, probably in civil, all these other engineers, are second-order differential equations that are homogeneous. We're not going to cover that here. This is a very basic class. It's not meant to be that hard or difficult. Follow me, class? First-order transients only. So when we talk about inductors in general, what year are they going to fix this? They had to order a thermal sensor. Is it? Anyway, let me see. The age-old problems. This is a brand new marker, by the way. At least it's right out of a new box. Some things just don't work the way they like. Let's try something else. I hope one of these works. All right, let me know if you can see this, because if not, I'll borrow a marker from someone. You got to be kidding me. This is another new marker. Obviously, new markers aren't made very useful. All right. Anyway, this is an inductor. It's like it's a joke. Somebody's pumping it. All right, that's an inductor. This is a resistor. I'm going to do it as simple as I can, show you the differential equations and give you the simple thing. Can everybody see that? Inductors have the units of henries, and the symbol is L. In the far back, guys, you good? All right, the resistor, of course, is here, R. Now, you have to assign polarities and directions for currents and voltage. If you don't know what you're doing. So I always take the current, if I have a choice, I try to make it to go clockwise. That would be I of t. Everybody with me on this, class? Now the voltage across an inductor, across that inductor as a function of time, is L di dt. The polarity is sensed in the direction the current enters, you put a plus sign, and the direction it leaves, a minus sign, and that is the voltage across that inductor. Do you all follow me in this class? Now the voltage across a resistor will be plus to minus, and of course, this voltage will just be I of t times R with the polarity shown. Does everybody agree with this, first of all? How many see this? Can you see it in the far back? I always worry about you guys. You with me? Now, if you look at this, some people are asking, do we have to write the differential equations every time we solve? No. You go through the steps I outlined before. Remember? There are 4 basic things you did. It's going to be the same with inductors. But for completeness, we have to write the equations, differential equations, and then solve them one time. So if you do this and we go around the loop, this is a voltage drop, right? If you start here and go this way, it goes from plus to minus, you're losing. So it's going to be minus L di dt. And then what about here? Minus, right? You're going through the resistor, it's going to be a reduction. How many see that? You don't have to always amen me, but just let me know, at least with a polite nod, that you got it. All right, so it's minus R times I, and it's really I of t, but I tend to be a little sloppy with that. It equals 0. Can everybody follow me? That's straightforward, just like in physics. I'll multiply by a negative sign both sides to get rid of them. Then I'll divide by what? L. Correct, class? Now we have this. Now that's di dt plus r over L I of t equals 0. First order differential equation. It's homogeneous. You all follow me, class? How many remember these from, I don't know, math, your engineering courses? It is the most fundamental equation as far as a differential. The solution is what? We can do this. We did this before with VS, didn't we? I took one thing to the other side, then I divided I of t by di, or a di by I of t, right? And then integrated, and you got a natural law. All right, after all that is done, this is rudimentary. You get I of t, the general solution will be equal to some constant that I'm going to just call I naught. That's the current flowing at t equals 0. I think you remember there was a V0 kind of thing. There's a voltage just as the switch closes. Do y'all remember that? With inductors, it's always the current that doesn't change instead of the voltage when the switch closes. I'll be clear about this, and I'll do problems so everybody sees it. It's going to be that, then it's going to be e to the minus t over tau. Here, tau is equal to L over R. Now, the other tau was equal to R times C. Y'all remember that? Here's how I remember this. You're wondering, is it L over R, R over L? The time constant is always larger as the value of either capacitor or inductor gets larger. So it's always going to be proportional to L or C. However, with capacitors, it's R times C. With inductors, it's L over R. Just like that. You all see that, class? Okay. Do you remember this from physics, guys? How many do? I don't know how your physics teacher did this, but usually they start with a differential equation and solve it. Usually. Okay. Now that would be true if there are no sources in the circuit. Now let me give you an example of this. Forget how it happened. If there was a current flowing there at t equals 0 that somehow we knew about, that would be your I0. And you see it decays to 0, right? If there's no sources, no voltage or current sources left in the circuit after the switch transitions, it goes to 0. It has to. Remember with a capacitor, the voltage goes to 0 if there aren't sources. Do y'all remember that, class? Same deal here, only it's going to be current. Now, if there were sources, then you would have to add a constant. As a matter of fact, what I'll do now, I'm going to say this, and I hope you can follow me on this. I'm trying to show you the similarity between the inductor's equations and the capacitor's equations. Capacitor voltage, inductor current. Usually we did what? We called this K1 before with capacitors, right? And it's plus K2. What was K2 if we're talking about the voltage across the capacitor? Anybody? It's what?
0.
Well, yeah, but ultimately, if there is a source, it is the voltage at t equal to, y'all with me? That K2 here would be the current flowing through the inductor at t equal infinity. That's the difference. You all with me on that, class? Show of hands if you understand this. That's the parallels, and it's important that you see them. Now, in this particular case, this K2 is 0, but this is now here I'm telling you, this is the general form of the equation that you go for. This is it. The time constant, K2 is the value of the current as t equal infinity, and you find out what K1 is by the value of the current when it transitions, when the switch changes from 0 minus to 0 plus. And I want to tell you something, because in the back of your mind, you're always suspicious. Am I going to try to trick you? This switch will always do its business at t equals 0. I'm not going to have it switch at t equal 1 second. You follow me? There's no tricks here. I'm trying to make sure that everybody sees the thing. This is not a class for electrical engineers or anything like that. You're supposed to get the fundamentals and only the fundamentals. Now you're going to have to deal with circuits like this because these are timing circuits. How many have seen RC or RL circuits as timing circuits? Surely you have. Are you Emmy? And what class did you see him, if you don't mind me asking? Where did you see him?
A little bit of physics too.
Physics 2? Well, they're used a lot of times for timing circuits, and I'm not going to get into it, but what they know the discharge rate is a certain value. So they'll look, when it's fully charged, to the time it goes down to like half charge, the time that takes, there'll be something that senses it, and it'll be a transition. So it's a very good timing circuit. They are somewhat sensitive to temperature though. You have to be careful about this. Now, some other things about this that I have to make clear. You know, a capacitor, let me take a step back. How many remember inductors in physics? You don't really? You didn't have inductors? Are you kidding me? How many have had inductors in physics? Try to be honest this time. If you didn't get it, then I don't know why you're here, because this is one of the things I get. They've had inductors, they've had capacitors, they've had physics 1, 2, and 3, I think, right? You've had that. Well, with an inductor, what is an inductor? Anybody want to tell me in your own words? You all know it, I think. Think of a coil of wire. Take just a bunch of wire and wrap it around a piece of iron core. That'll create an inductor. It's something that stores magnetic energy, not electrostatic energy. A capacitor stores electrostatic energy. You have charge differences on the plate. They create a voltage, and the actual value of the energy stored is 1/2 CV squared. Does anybody know what the energy is in an inductor? If the current's flowing. Anybody? No show-offs in here, huh? 1/2 Li squared. It's proportional to the current squared, inversely and directly proportional to the value of inductance. Just for completeness, if you have an inductor with L and a current I flowing, the energy is 1/2 Li squared. What are the units of energy? Joules. Thank God. I have, obviously, I'm not fond of steam tables and unit conversion. That's my weak spot. Anyway, that's what it would be in joules. For a capacitor with a voltage V across it, or some V naught of C, the energy here is 1/2 CV squared. Some of you are going to think, do we have to know that for the exam? No, but I'm trying to give you some general understanding. So it's always proportional to the square of either the voltage or the current, depending on the element, and it's directly proportional to the value of the element. You all follow me? That's one thing at least you should take from this. Okay, next, what we're going to do is talk about what the inductor looks like if nothing's changing with time. This I want to be clear about. When you do problems, all of a sudden you see this stuff. So remember, if I have this as the symbol I use for the inductor, and I have a current I of t flowing, it develops a voltage V here equal to L di dt. This is key, right? Remember, that inductor is just a whole bunch of turns of wire. That's the way you think about it. Well, if nothing changes with time, the resistance or the impedance, whatever you want to call it, how it looks, in other words, this time, if nothing changes with time, is like a short circuit. You see, if the IDT is 0, the voltage is 0. Everybody follow me? It looks like a piece of wire. That's it, just a straight piece of wire. But the faster the time-changing current is, the larger this voltage. What that means is you cannot have instantaneous changes in the current. It would cause an infinite voltage. You all follow me, class? That can never be. You can't have instantaneous changes in the current. It's impossible. Something that goes from 0 to infinity. You know what, like a Dirac delta function is unit step, right? At 0, 1 kind of stuff, you can't have that here. It would cause, for current, it would cause an infinite voltage, which is not possible. You all with me, class? Just remember that. So the idea is, if nothing changes with time, it looks like a short circuit. But the minute that switch closes, it looks like an open circuit at that instant next to it. You follow me? Because then it's trying to make a change instantly and it can't. So I'm going to go through some problems that I think you'll see. You with me, class? By the way, as t equals infinity, what would the value, if you thought about it, would look like an open circuit or short circuit? Think dIdt, that's time changing. Is anything changing as t goes to infinity? It looks like a short circuit. You all follow me, class? So let's do a few problems and acquaint you with this, and I think you'll pick it up pretty fast. Hopefully. I'll get to your problem now, but I needed to give you that background. By the way, how many went to the game? How many got drenched? I heard more about rain ponchos and how I wished after the game than I think I've heard ever, well, in a long time. Anyway, I hope Arkansas is going to be ready, because I'm going without. All right, you ready? Which problem is this? What?
4.38.
438. All right. All right, 4.38, let's see if I can find it. All right, by the way, these circuits will always have a lot of resistors in series or parallel, reduce them in complexity. I've got to show you how to get R Thevenin across this inductor, but it's the same thing as R Thevenin across the actual capacitor. The same thing. You'll see this, I think. So this is 4.38. Here, got 24 volts. Then you have 2 Henrys, or 2 ohms. Then you got a switch, and the switch opens at t equals 0. We'll go through this and I think you'll see it. Then you have 3 ohms. And you have an inductor. And the inductor has a value of 2 Henrys. Then you have 2 ohms. And you have 4 ohms. And what do they actually want? They want this voltage. And this is 4 ohms. And they want this voltage. Now, just like the capacitor problems, you could care less about what they want. The only thing you care about is the current through the inductor. That equation, you got that? Once you have it, everything else is solvable from that information. So the first step is, let me put the equation up here, let me put down the steps. What the steps are is this. First, you find I through the inductor for t less than or equal to 0. In other words, before the switch transitions. So you need this information. The second thing you do is find the current through the inductor as t goes to infinity. In both of these cases, the inductor will appear as a short circuit. I'm going to slow down and make sure you grasp this. You all with me? After that, now you need the Thevenin equivalent resistance across that inductor. If you ripped it out of the circuit, what would you measure? Do you all follow me? This is after the switch transitions, though. Go ahead, Sydney, ask me. What can't you read?
The second one, I.
It's I of L. Yes, my handwriting is terrible. I'm going to put just I sub L. It's just the current through the inductor. Can you all see it in the far back, guys? Everybody? Now, R Thevenin is just like before. The time constant is different. So right here, you might as well just put it here. Time constant is now L over R Thevenin. I think in the first part, or when I was talking about initially, I didn't put TH. It's the Thevenin equivalent resistance. Now, once you have that, then you put the whole thing together and solve this. IL of T equals And I'll just use K, so it's K1 e to the minus t over tau plus K2. Here K2 would be the value of the current as t goes to infinity. I want to make sure we're clear on this. This is not hard. You just have to be attentive. Everybody with me? Okay. Now, we're going to go and we're going to start for t less than 0. Follow me? T less than 0, that switch has been on, right? This will look like a short circuit. You all follow me in this class? How many do? Because nothing changes with time, the voltage is 0. You might as well just put a wire there. But I'll indicate what I'm talking about. Let's see if I can get this here. So what you have is 24 volts. That's that. Then you have 2 ohms. Then you have 3 ohms. And here's where the inductor was. And I'm going to call this current through the inductor positive. You all with me, class? Everybody see this in the back, guys, okay? I want to make sure you understand the direction of current I'm choosing, going down. All right, so I just put a wire there. And that's the current I want. I want this current right here. I'll call it IL for t less than 0. But there are these 2 resistors here. Can you see that? So I'm going to combine them. Can everybody see the 2 and the 4 are in series? Give me a show of hands so I know. Over here, you guys good with that? With me? They're in series. That's 4 ohms in series with 2 ohms or 6 ohms, right? Now remember, I want this current. I don't care about that current, just this current. You all follow me? Well, you can do it a lot of ways. Personally, the way I usually do these, I'm going to say I got 3 and 6. That's equivalent to 2 ohms, isn't it? In parallel, they're in parallel. Do you agree with that, class? Make sure. How many see it's parallel, those 2? So I'll make that 2 ohms in series with 2 is 4 ohms. Do you agree with that? I've got 24 volts. 24 by 4 is how many amps? 6, that's right. Are you all with what I'm doing? How many understand what I'm doing? I'm trying to just get what? This current right here. So this current I would be equal to 24, I'll call it, well, just I source. 24 over, and that is 2, that's 2, 4 or 6 amps. All right, you got the current here, but how do I get the current here? How would you do it? How many see current division is probably the easiest? Far back, guys? All right, what would it be? That means my IL, and I'll put it right here. For t less than 0, I got a total current of what? 6 times what? Current division says take the opposite resistance, correct, class? Divided by the sum of the 2. 6 over 9, or, oh, put 6 over 9. So it's going to be 6 over 9. Does everybody understand how I'm getting this? If you do, let me see your hands so I don't want to lose anybody. Does anybody not see what I'm doing? You don't see it?
Yeah, where did you get that 4 on the 24?
You see that 3 and 6 in parallel, right?
Yeah, you just combined.
That's 2 ohms. I mean, I'm making sure there's no dumb questions here. You might have missed something. Just make sure you see every bit of it. Everybody good with that? So that's going to be what? 2/3 times 6 or what? Do you understand what I'm doing here? So this is 4 amps, correct, class? Now we've got that. We've got 4 amps. We can check that box. Now, first, is everybody with me? Now I'm going to let the switch change states. When it changes states, effectively what happens when I do this? It opens. Anybody, say it in your own words, what happens? You basically decouple. This whole thing's not here anymore. You all see that? Because it's only connected at one point. How many see that? I'm going to erase it. Makes my life easy. Now, and give me the reason, what's the current as t goes to infinity? Why? No batteries, no current sources, no problem. It's 0. Everybody see that? So it's 0. That's it. So this goes to 0. Life is good. What about R-thevenin? This one's an easy one. Now, some of you struggle with this. I try to make it as clear as possible. I'm going to erase this. Here's two dangling points. If I had a ohm meter that I would stick across there, what value of resistance would I measure? They're all in series, right? 9. How many see it's 9 ohms? You guys see it? With me? I want to make sure I don't see a whole lot of hands. Does everybody follow me on that one? Anybody not follow? All right, 9 ohms. All right. What's R-thevenin? I forgot what the inductor was. What's the value in inductance for this one? Pardon me?
2 Henrys.
2 Henrys? All right. What's the value of the time constant? 2 over 9, and that would be correct. Y'all with me, class? Now, the units of the time constant are seconds, by the way. So now we put the whole thing together. Are you ready? I want to make sure everybody sees this. I'll stop for a second and see people writing. Who has tablets? A lot of you people have. If I need to slow down, please just let me know. Okay? All right. Come back to this thing. Now, this is the equation. What is K2? Can you see it there? How many see it 0? There ain't nothing there, right? And infinity, so that makes life easy. Now, if K2 is 0, what must K1 be? Has to be the current. It's T equals 0, right? 0 minus. Follow me, the current can't change instantaneously. So that current is 4 amps. Now, you all see what I'm doing? So technically, this current, IL of T, would be 4 e to the minus T over the time constant. I'm just going to leave it as time constant. It's too nice. You all with me, class? I don't really need to put that in there. Okay, that's the circuit. I mean, basically we have this now. After all is said and done, you might as well, I can put the inductor in, but it doesn't really need to be here. I know that this current, I'll put it this way, that current right there is actually equal to 4 e to the minus T over tau. We know tau is too nice. Do you agree with that? How many see that? Now it's very important you see this. Notice the direction going down, right? That means the current, this current is going this way. Correct, class? So what is that volt? You asked this, who asked this question? So what is this voltage going to be? Now what I suggest is before you take a look at that voltage, if you were asked what the voltage is across that 4 ohm with the polarity, I expect you to say, well, the current's coming in here. It would be plus to minus, and this voltage that I'm showing you here would be what? The actual current the resistance 4 times the current, times 4 e to the minus T over tau. But notice the polarity. Does everybody follow me on that? Take a moment. How many see that? You know the current through the inductor. That's the only possible current flowing in that circuit. Are we clear on that, class? If that is the case, then that would be the voltage. 16 e to the minus T over tau, right? Tau is 2 nines. But the actual voltage they want is what? Have the opposite polarity. This is the polarity they wanted, right? How many see you just put a negative sign there? In the far back. Do you all see this? Over here, guys? I know some of you are right. I mean, do you see it or not? If you don't, we need to talk about it. So this really, the actual voltage that he wanted, V out of T, would be equal to minus 16 e to the minus T over, and then it would be 2/9 if you wanted to do it like that, volts. With me? Is that the right answer, by the way?
I think it is, yes.
Can anybody confirm or deny this?
Yeah, that is the correct.
All right, you follow the trick on this one? So similar to the actual steps we did for capacitors, except this time we're looking for current. You ready to do another one? I think the best way to do them is, this is my advice to you. You want to feel confident and do well? Do a lot of problems. Do them without looking at the solutions. Whenever you mess up, learn from it and keep going. You can't really do too many problems. All right, we do another one. Now, I'm going to do one, maybe not this one, but the next one with a source left. So the voltage or current will not, then there'll be some sources left. You all follow me? So K2 will have a value. Everybody with me on this? So the next problem, is anybody got a problem? Anybody got a problem they want me to work first? I gave you some. Nothing? Okay. Let me pick one. I'll tell you what, I'm going to do one with a little trickier. And then I'll do one with an actual source left over. This is 4.42. Did I assign that one? I don't remember. Maybe. All right. 4.42. So here, he's got a current source of 6 amps. Then he has a switch. And the switch closes at T equals 0. Then he has this stuff. He's got 3 ohms. He has 6 ohms. Ohms. And then he has an inductor of 2 Henries. And he actually wants this current. That's what he's after. Oh, this might be good. Okay. You all following on that? So what we're after first is I flowing through that inductor for t less than 0. We're going to get that in 1 second. Second thing is I in that inductor as t goes to infinity. Third thing is R Thevenin and the time constant. All right, then we'll put the whole thing together, but I'm going to just write them down like that. I think you probably know what I'm up to. Everybody with me? Now for this, what I want to do first is redraw the circuit, how it looks for t less than 0. That's the key thing. So for t less than 0, that switch is open, right? So that means I have this. I have a current source here. That current source is 6 amps. Then I have a resistor of 3 ohms. And then I have 6 ohms. Oh, sorry. 6 ohms. I'm just going to leave it 6 ohms. And then I'm going to take that 12 ohm and put it vertically downward. And here's my inductor. And I'm going to call this positive current, I of T here, through the inductor. All right, and what I'm really after is this current. Y'all follow me? How many see that's the circuit? Back there, can you guys? Okay. Now, this is meant to be easy, but some people are suspicious. How much current's going through that 3 ohms? 6, right? I mean, it's given. It's the only way it can flow. As a matter of fact, let me ask you this: how much current is going that way? It's the same. Y'all with me, class? Like incompressible fluids. All right, there's 6. Do y'all see if I want? Remember, I want the current through the inductor. I know they want that, but I don't care about that. I only care about the current through the inductor. This is the key thing to take, the big takeaway. So how do I get this current? Right here. You know what? 6 amps is flowing into 2 that are in parallel. Is it not, class? How many see that? So if you want the current flowing here, you take that 6 amps and you multiply it by the opposite resistance and divide it by the sum of the 2, right? Or 18. Is that not right, class? What do you get for that? 2 amps, right? So that means first, you all see this. You good with that? 2 amps. Okay, so we're good for t less than 0. You give me that? Now watch this, because this is the one that will catch people. Now I'm going to take a look at the circuit, and I'll have to draw it there for t greater than 0. So I want to erase this, make sure you see it. All right. Now, when t is greater than 0, that switch closes. This is something that's very important you see. When that switch closes, I'm literally going to take it out and do this. Can you all see that? Now, what I've just done is what? I've taken this current source, I took the top part, connected it to the bottom, right? How much voltage is between these 2 points? 0. By definition, it's a straight wire, right? I don't care if current's flowing. So to get a better feel for this, so you can see it better, what I'm going to do is this. You see how electrically that is the same exact circuit? Y'all follow me? Because there is no voltage between the top and bottom of this. What's actually happening is this current's just circulating there. None of that current is going to influence the other circuit. Y'all follow me? As a matter of fact, now listen. I'm going to reorient that resistor so it's very obvious. Can you all see I can do this? How many see that? No? Are you good with that or not? It's electrically the same connection, isn't it, class? How many see that, really? It's very important you do. Now, if that's the case, right here, without going any further, what is the current as t goes to infinity? How many see it's 0? There are no sources here. You all see it? What people do, they're suspicious that thing's still there. It doesn't matter. It's fundamentally disconnected. It's connected only at one point electrically in terms of a potential difference. Can you all see that? That's very important, which makes my life easy. It's that, right? Now, what you catch yourself doing is you're writing equations and you're solving this current. Don't solve that current, you're solving that current. Got it? So now we need R Thevenin. So if we want R Thevenin, I want to see how many people see this. Just imagine you take the inductor out. How much resistance is between this terminal and this terminal when the inductor is out? Well, you know you have 12 ohms, right? Plus what? 3 in parallel with 6 is 2. 14 ohms. How many see it's 14 ohms? Now take a look. Be suspicious of me. I could have made a mistake. You see that? These 2 are in parallel, 3 and 6 in parallel. I don't care how you do it. 1 over 3 plus 1 over 6. That's really 2 over 6 plus 1 over 6 is 3 over 6 or 1/2, flip it, 2 ohms, right? 2 ohms and 12 ohms is 14 ohms, I hope. Right? So 14 ohms. What is our Thevenin? What was the inductor? Right? 2 Henrys. So what is that going to be? Can you all read this or not? I guess it's not big enough. It'll be big enough in one section. One second. Tau is equal to L, right, over R Thevenin, right? Or 2 over 14, 1/7. You give me that? 1/7. All right, now put the equation together. I have IL of T equal, what is it now? 2, right? I mean, you follow me? We could write the equation K1 plus e to the minus T over tau plus K2, but K2 is 0. Is it not, class? How many see that? The current goes to 0, so I'm not even going to write it. That means the current that's going to be here is really a current that T equals 0 plus and 0 minus. They are the same. They can't change instantly. And that happens to be 2 amps, so it's 2 e to the minus T over tau amps. Now that's the current flowing here. Y'all with me, class? Take a moment, make sure you see this. If that's the current flowing there, what is the current flowing here? If you don't see it right away, here's what I recommend you do. Don't worry about that current, because that's going the wrong way. Suppose I wanted this current. I'll just call it I prime of T. How would you get that current? Anyone? I'm going to see current division works. All right? Now you have a current. We know that current. We know the current going into the parallel combination of those, don't we? Right? So if I want this current, and I'm having it going up in purpose so that you can see a little better. So now I can say, well, my I prime of T here would be that current IL, 2 e to the minus T over tau. Then it's times what? The opposite resistance, 3, over the sum of 3 and 6, or 9. Or it's simply going to be 2/3 e to the minus T over tau amps, right? But that would be the current going this way. Can everybody see that? Show of hands if you can see it, so I'm sure about it. In the back there, can you guys see it or not? The guy who's giggling, can you see it? I'm just making sure. Yeah, with the laptop. I'm trying to help you, trust me. I'm not trying to put you on a spot. You need to focus on this because this is where mistakes are made. So if you know that's the one going up, going down is negative. That's it. So if you want I naught of T, minus. How many see that? Got a question for you before I move on. What if I wanted this voltage right here? What would it be? I mean, the actual current we have is what? The current I just showed over there, I naught of T, is this, right? I ask this all the time. I don't ask for just current, I ask for voltage, usually multiple components on the quizzes. So what's that going to be? It's that obvious. 6 times I naught of T, right? How many see that? Are you with me, class? It would happen to be negative. What if I wanted the voltage across here? 12 times IL of T. It's really that simple. Do y'all follow me, class? All right, let's do one more, and this time hopefully with a source, okay? Have you got one for me? Let me know. Or something where the current is not going to go to 0 T form. So I'm going to do 4.44. Now, this isn't that tough a problem, but you have to see the steps. So I'm going to erase this. All right. Everybody's leaving. Is it something I said? Anyway, if you look at this thing, just think for a second now. Anyway, if you look at this for t less than 0, just give me your attention. What is going to be the current through this inductor? I bet you can see it. T less than 0. That switch is, it's a short, right? If it's closed, you see that that part of the circuit is isolated from this part. How many do? What's the current at t less than 0? Zip, 0. I'll just write it down. Now, you all see that? What about when t, now I'm going to go to t equals greater than 0. It looks like this. Do you agree with that, class? Show of hands if you do. Let's try to simplify this over here. I got 6 and 6 is 12, and parallel with 6 is 4. Make your life easy. It's hard enough without this kind of crap. You agree with that? How many say it? All right, keep going. Now, what's the current through that thing at t equal infinity? I don't have time to go through every step. How many see the total resistance is 8 ohms? Show of hands. Because the inductor is a short circuit, correct? All right. If you got 24 volts and 8 ohms, how much current? 3 amps. Show of hands. 3 amps have it. All right. What's our Thevenin? Now here you have to use Thevenin equivalent. What do we do with a voltage source if we? Now I'm just going to rip it out. When I take that out, what is the Thevenin equivalent resistance across those two terminals? Class, what do we do with a voltage source if we want Thevenin? Class, short circuit, get rid of it. What's Thevenin equivalent resistance? 8 ohms. Can you get tau? L over R. Can you finish it? Yes. I'll give you a bunch. Please be sure to do them.